Okay, hello learners, welcome to session 6 of unit 5. In the previous session, we looked at how to represent complex numbers in exponential form. In this session, we are going to talk about De Moivre's theorem and the end root of complex numbers. I am Mukaila Dasmani, your course instructor. So in this session 6, we are looking at De Moivre's theorem and the end roots of complex numbers. By the end of this session, you should be able to calculate n power of any complex number z and also find the nth roots of a complex number z. Okay, now let's see here. You learned in session 4 that any complex number z can be written in the polar form as, okay, let me take my marker, so my pen, and name it equation 1 as equation 1. That's why we learned already that any complex number can be written in this form. Don't forget about your Euler's formula approach. So the De Moivre's theorem gives a formula for finding the nth root or nth power of any given complex number. So when any complex number z is given, then with the help of the De Moivre's theorem, you can use it to find the nth root or the z raised to the power n. Okay, so from equation 1 here, when I square both sides, so z square is r square, then cos 2q sine 2q. Z cube, so you see the way it is following. Z cube equals to r cube cos 3q plus I sine 3q in that order. So what do you think will be z power n will be what? Okay. So theorem 7, De Moivre's theorem. If z equals to, we've already talked about that, r bracket cos q plus I sine q, and n is positive integer, then I ask you to think of that. Z raised to the power n, what do we get? So z raised to the power n is actually the same as the expression raised to the power n, and then it becomes n r raised to the power n cos nq plus I sine q. So in summary, so this one is what we call De Moivre's theorem. Z raised to the power n is equals to that. In summary, to find the nth power of a complex number, take the nth power of the modulus and multiply the argument by n. So simple like that. So that's the De Moivre's theorem. So the De Moivre's theorem is named after the French mathematician Abraham De Moivre. So may his soul rest in perfect peace. He was from 1667 to 1754. 1667 to 1754, as I said. So think of this great mathematician. So what are you also going to leave it for us so that we can name after you? Maybe you get Cauchy's theorem, Cramer's theorem, Cancer's theorem. Yes, so think of that, very necessary. So we look at example 12. We want to find half plus half I exponent 10. So what do we do from here? So in the first place, we find the r. I know that you can find your r, and don't forget square root of half square plus half square. You get square root of 2 divided by 2. Also, you can also find our argument. Our argument will be the argument of, let's say we represent this one by z, or let's say argument of half plus half I. How do I get? Don't forget they all lie in the first quadrant. So half on half is 1, tan inverse of 1, or arctan of 1, you get your pi on 4. Pi on 4, you get your pi on 4. Therefore, what do? You have to represent this in polar coordinate first. So the expression in polar coordinates. So half, let me say that let z equals to this, so that becomes very simple for me. So let z equals to half plus half I, half plus half I, and then we can go ahead, we solve for z, and then after that we can do the rest. So it implies that z is now equal to, you represent this in the polar form, and don't forget your r multiplied by the cosine of the angle and then I sine of the angle. I hope you remember that. Cosine of pi on 4 plus I sine of pi also on 4. Okay, so then we go ahead. Once you've been able to express the function in polar form, what will be the next? The next is by using the De Moivre's theorem. So by using the De Moivre's theorem, we have half plus half I power 10 equals to, I could also write z power 10. So what do I get? R with power n, and that is square root of 2 all on 2 power 10 bracket open cos n q, that's 10 times pi on 4, I get 10 pi on 4 plus I sine the same thing 10 times q, so I get 10 pi on 4. Okay, this is actually 1. Yes, this is 1. Okay, let me clean that place and write it so that it's okay. So you get cos 10 pi on 4 plus sine 10 pi on 4. Actually, I write big. Okay, so that is using the Moivre's theorem, you get something like this. Then you can simplify this further. Don't forget about cos 10 on 4. So you get 0, and then so in conclusion you get 2 raised to the power 5. That is, you use law of indices, or divided by 2 to the power 10 to get your I first. And then in that instance you get what? You can use the law of indices again. 2 to the power 5 on 2 to the power 10 to the power negative 5. And 2 to the power negative 5, that's 2 to the power negative 5i, or same as 1 on 2 to the power 5, 2 exponent 5i. Okay, so let's do this simple calculation. You are free to go. You get the answer. So the nth root of a complex number, and this one, the nth root of a complex number z is a complex number w such that w exponent n equals to z. So if I ask you to find w, what do you get? So the w will be equal to, let me take pen and then, alright, the w will be equal to the nth root of z, the nth root of z. So in that instant, you're saying that you'll find the nth root of the complex number z. So the derivation of this nth root formula is very simple in your course material. So I leave that one for you to check it and then find how the formula is derived. So section review, find the 6th root of z equals to negative a. So after deriving the formula, then you use that one to find the 6th root of this complex number.